What if the next giant leap for humanity isn't up into the stars, but down into the Earth itself? We often dream of colonizing Mars or building bases on the Moon, but some of the most revolutionary technologies for our future might be hidden right beneath our feet, waiting in the dark, silent depths of the underground. Picture this: vast networks of tunnels humming with advanced machinery, subterranean habitats shielding us from cosmic radiation, and laboratories buried deep below the surface where scientists unlock secrets about life in extreme environments. These aren't scenes from a sci-fi movie. They're real projects being developed right now, and they're closer to deployment than you might think. The underground has always been a frontier of mystery and potential, but today it's becoming a testing ground for technologies that could redefine how we explore space, harness resources, and even survive on other planets. Think about it: if we can master living and working underground on Earth, we're one step closer to thriving on the Moon, Mars, or beyond. And it's not just about survival. These innovations could revolutionize industries, from mining and energy to urban development, solving some of our biggest challenges right here at home. The irony is delicious. To reach the stars, we might first need to dig deeper into our own planet. So why aren't we talking about this more? Maybe because these breakthroughs are happening quietly, out of sight, far below the headlines. But that's about to change. In this video, we're uncovering 21 underground space technologies that are shifting from blueprints to reality, some already in prototype, others on the brink of deployment. From autonomous tunneling bots inspired by Martian soil, drills to geothermal energy systems that could power entire cities, these innovations aren't just futuristic concepts. They're proof that the next era of human progress is being built in the shadows, literally, ready to see what's lurking below the surface. Let's dig in. Underground habitats might sound like something from a futuristic novel, but they're quickly becoming one of the most practical solutions for long-term space colonization. Imagine stepping into a sprawling underground city on Mars, not a cramped, temporary shelter, but a carefully engineered network of tunnels and chambers, shielded from the deadly radiation and extreme temperature swings of the surface. Unlike flimsy surface domes vulnerable to micrometeorite impacts, these subterranean spaces offer natural protection, mimicking the safety of Earth's deepest caves. What's fascinating is how scientists are drawing inspiration from Earth's own extremes to design these habitats. Research teams are already testing prototypes in places like volcanic tunnels in Hawaii or the icy depths of Antarctica, in environments that mimic the harsh conditions of the Moon or Mars. Some designs even propose repurposing natural formations like lava tubes, massive underground caverns left behind by ancient volcanic activity. These ready-made tunnels could serve as the perfect foundation for habitats, saving time and resources while providing instant structural integrity. The real game changer: autonomous robots that could do the heavy lifting before humans even arrive. Picture AI-driven excavators and 3D printers carving out living spaces, reinforcing walls with locally sourced materials, and setting up life support systems, all without direct human oversight. NASA and private companies are already developing tunneling machines inspired by Martian soil drills, capable of digging, analyzing, and even building as they go. But underground living isn't just about survival, it's about creating a sustainable future. These habitats could house vertical farms using advanced hydroponics, recycle air and water with closed-loop systems, and even generate power through geothermal energy. The lessons learned here won't just help us live on other planets. They could revolutionize how we build resilient cities on Earth, especially in areas prone to natural disasters or climate extremes. The idea of burrowing beneath the surface of another world might seem strange at first, but when you consider the alternatives, it's one of the most logical steps forward. Underground habitats could be the missing link between short-term missions and permanent colonies, turning science fiction into science fact faster than we ever imagined. Giant mechanical moles could become humanity's first construction crew on other worlds, operating silently in the darkness to prepare our future homes. These autonomous tunneling machines are engineering marvels, combining cutting-edge robotics with artificial intelligence to chew through rock and soil at staggering speeds. On Earth, they're already transforming urban infrastructure projects, but their true potential lies in off-world applications where traditional construction simply isn't possible. Take the boring company's Prufrock drill. It can tunnel faster than a snail moves, about 1 mile per week under ideal conditions. Now imagine that same technology scaled for lunar regolith or Martian bedrock. Unlike Earth's complex geology, these extraterrestrial environments present unique advantages. The Moon's lack of atmospheric weathering means its subsurface layers are more uniform, allowing AI diggers to operate with predictable efficiency. Some prototype machines even incorporate microwave drills that vaporize rock instead of grinding through it, perfect for low-gravity environments where conventional methods would struggle. What makes these machines truly revolutionary is their ability to work without human oversight. Equipped with advanced sensors and machine learning algorithms, they can map tunnels in real time, adjust digging patterns based on mineral composition, and even perform basic structural reinforcement as they go. NASA's moon diver concept envisions robots rappelling into lunar pits to explore lava tubes, essentially nature's pre-built underground habitats. Private companies are taking this further, developing systems that could 3D print tunnel linings using local materials, creating airtight living spaces ready for human occupation. The implications go far beyond simple excavation. These autonomous diggers could create entire subsurface networks connecting habitats with pressurized passageways, carving out underground farms with optimized sunlight channels, or even constructing massive radiation-shielded storage facilities for fuel and supplies. Some designs incorporate modular components that allow a single machine to switch between drilling, analysis, and construction modes, the ultimate multi-tool for off-world development. Perhaps most exciting is how these technologies feed into each other. The same drills that create underground bases could tap into geothermal energy sources, while their waste material becomes feedstock for 3D printers manufacturing tools and spare parts. It's a closed-loop system where every action serves multiple purposes, exactly what we'll need for sustainable extraterrestrial settlements. While we marvel at rockets and surface habitats, these unassuming robotic miners are quietly solving one of space exploration's toughest challenges: how to build permanent infrastructure without bringing all the materials from Earth. They may not look glamorous, but these mechanical diggers could be the foundation upon which our interplanetary future is built. Beneath the surface of planets and moons lies an untapped solution to one of space exploration's most persistent problems: energy storage. While solar panels work brilliantly in orbit or during daylight hours, they become nearly useless during the moon's 2-week-long nights or when Martian dust storms blot out the sun for months. That's where subsurface energy storage steps in, turning the very ground beneath our feet into a giant battery that could keep colonies alive through the darkest periods. The concept is simple yet brilliant. Here on Earth, we already use underground caverns to store compressed air or pump water uphill for hydroelectric power. In space, similar principles could be adapted with even greater efficiency. Imagine a network of artificial caves filled with massive weights. When excess solar energy is available, robotic cranes lift these blocks to the ceiling. Then, during power shortages, the weights slowly descend, turning generators as they fall. This gravitational storage system, free from the degradation of chemical batteries, could provide decades of reliable energy with minimal maintenance. Researchers at the European Space Agency are already testing scaled-down versions of these systems, using lunar regolith simulants to create ultra-dense concrete blocks. The lower gravity on the Moon or Mars actually works in our favor. Here, less gravitational force means we can lift heavier weights with the same amount of energy, making storage even more efficient. Some designs propose using abandoned mining shafts or natural lava tubes as ready-made storage chambers, saving precious construction resources. But gravity isn't the only option. Deep underground thermal batteries are another promising avenue, using the insulating properties of rock to store heat at extreme temperatures. Molten salt could be pumped through subsurface reservoirs, retaining enough thermal energy to power steam turbines through long nights. NASA Kilopower project, originally developed for lunar outposts, is being adapted for underground deployment where the stable thermal environment boosts efficiency. The real breakthrough comes when these systems work together. A colony might combine gravitational storage for short-term needs with thermal batteries for sustained baseload power, all managed by AI that predicts energy demands based on weather patterns and activity levels. Early prototypes already show impressive results. One test facility in Iceland successfully powered a simulated habitat for 6 months, using only subsurface storage charged during summer months. Perhaps most exciting is how these technologies could loop back to benefit Earth. The same systems designed for Martian colonies might revolutionize renewable energy storage in remote areas or disaster zones. Underground thermal batteries could provide clean power to entire cities during winter months, while gravitational storage in abandoned mines might balance power grids relying on intermittent solar and wind. What makes subsurface energy storage so compelling isn't just its practicality, it's the elegance of using planetary geology itself as part of the solution. Instead of fighting against alien environments, we're learning to work with them, turning perceived limitations into assets. As these technologies mature, they could finally solve the energy puzzle that's held back long-term space habitation, proving once again that sometimes the best way forward is to dig deeper. Forget traditional farms under open skies. The future of sustainable agriculture might lie in windowless, climate-controlled chambers buried deep underground. Picture rows of vibrant greens and plump vegetables thriving without a single ray of sunlight, their roots bathed in nutrient-rich water, while precisely tuned LED arrays mimic the perfect growing conditions. This isn't some futuristic fantasy. Scientists are already perfecting these subterranean farming systems in some of Earth's most extreme environments, from the frozen deserts of Antarctica to the scorching sands of the Middle East. And the lessons learned here could one day feed colonies on Mars. The challenges of space farming are staggering. Surface conditions on the Moon or Mars, lethal radiation, toxic soil, and wild temperature swings make traditional agriculture impossible. But underground, crops are protected by meters of rock that block cosmic rays while maintaining stable temperatures. Early prototypes use hydroponic or aeroponic systems that require 90% less water than soil farming, with roots suspended in mist or liquid solutions packed with minerals. Researchers at the German Aerospace Center have grown tomatoes, peas, and radishes in simulated lunar soil. proving that with the right technology, even the most barren environments can become productive. What's truly revolutionary are the self-contained ecosystems being developed. Some experimental farms incorporate fish tanks where waste fertilizes plants, while the plants filter water for the fish, a perfect closed loop. Others use genetically modified crops bred for compact growth and hyper-efficiency, like dwarf wheat that produces full-sized grain heads in half the space. The latest LED arrays can fine-tune light spectra to boost specific nutrients in plants. Imagine spinach engineered underground to contain extra iron for astronaut diets. The most exciting breakthroughs come from real-world testing. In Antarctica's Noumea station, scientists harvest fresh greens year-round in a sunless farm, while Dubai's underground food caves produce thousands of kilograms of produce annually despite surface temperatures hitting 50 degrees Celsius. These facilities aren't just research projects, they're blueprints for off-world agriculture. NASA's Bionutrients program recently demonstrated how microbes could be activated to produce vitamins on demand, ensuring crops grown in sterile underground labs remain nutritionally complete. But the implications go beyond survival. These farms could become psychological lifelines for isolated crews, offering a touch of earth with fragrant herbs and colorful blossoms. Some designs even incorporate vertical, green walls that purify air while providing a sensory escape from the monotony of metal corridors. As these systems evolve, they might solve another critical problem: what to do with human waste. Advanced bioreactors can already convert organic matter into fertilizer, closing the loop in ways that could make Martian colonies truly self-sufficient. Underground farming flips conventional wisdom on its head. Instead of struggling to recreate Earth's surface conditions in space, we're learning to harness the stability of subsurface environments. The result, a vision of agriculture where control is everything, seasons don't exist, and every leaf of lettuce is a triumph of engineering over nature's limits. When the first Mars colonists bite into a salad grown beneath their feet, they'll be tasting more than food, they'll be savoring the future. Transporting tons of concrete and steel to the Moon or Mars would be astronomically expensive. But what if we could build entire habitats using nothing but the dirt beneath our boots? That's the promise of 3D printed underground structures, where robotic printers transform raw regolith into sturdy, livable spaces layer by layer. Picture a machine the size of a small truck, crawling through a freshly dug tunnel while its nozzle sprays a paste made of processed lunar soil mixed with binding agents. Behind it, curved walls rise like pottery on a wheel, hardening into arches strong enough to withstand meteorite impacts and radiation storms. This isn't speculative fiction, it's technology being tested today in deserts and labs that simulate extraterrestrial conditions. The secret lies in regolith's hidden potential. Lunar and Martian soil contain minerals that, when heated or treated chemically, can fuse into materials as durable as concrete. NASA's Moon to Mars Planetary Autonomous Construction Technology project has already printed test structures using simulated regolith, proving that walls just 15 centimeters thick can block 99% of cosmic radiation. Some printers use microwaves to sinter soil particles together, while others employ binder jets that work like industrial inkjet printers, depositing liquid hardening agents precisely where needed. The European Space Agency even demonstrated printing entire parabolic domes in a vacuum chamber, mimicking the Moon's airless environment. But the real breakthrough is autonomy. These printers don't just follow blueprints, they adapt. Equipped with ground-penetrating radar and AI, they can analyze local soil composition on the fly, adjusting their mixtures to compensate for variations in mineral content. Some prototypes can harvest their own materials, using robotic scoops to feed raw regolith into onboard processors that filter out unwanted particles. Others incorporate recycled astronaut waste products, turning plastic packaging into reinforcing fibers that strengthen printed structures. Imagine landing a single printer pod on Mars that could spend months quietly building before humans arrive, carving out living quarters, workshops, and storage vaults, all while using local resources to minimize Earth dependence. The applications go beyond habitats. The same tech could print radiation-shielded greenhouses with built-in irrigation channels, or even underground launch pads with ramps angled for low-gravity ascents. Back on Earth, these techniques are already revolutionizing disaster relief and remote construction. Companies like Icon use similar 3D printing to build hurricane-resistant homes in hours, while researchers explore printing emergency shelters in war zones using rubble as feedstock. The lessons learned there feed back into space tech, creating a virtuous cycle of innovation. What makes this approach so transformative isn't just the savings in transport costs, it's the shift in mindset. Instead of seeing alien landscapes as obstacles, we're learning to work with them, turning barren soil into the very fabric of our future homes. When the first Mars colonists walk through arched corridors printed from the rust-colored dirt outside, they'll be living proof that the best building materials aren't shipped, they're excavated. The hunt for hidden water beneath alien surfaces might be the most critical treasure hunt in human history. While images of barren lunar plains and rusty Martian deserts dominate our imagination, orbital scans reveal a startling truth. Vast reservoirs of water ice lurk just below, locked in shadowed craters or embedded in porous rock. These aren't mere scientific curiosities. They're potential lifelines for future colonies, offering drinking supplies, breathable air through electrolysis, and even hydrogen fuel for rockets. The challenge: extracting this precious resource without hauling massive equipment across space. Breakthroughs in subsurface scanning are rewriting what's possible. Radar instruments aboard orbiters like NAS, a lunar reconnaissance orbiter, can detect ice deposits several meters down by analyzing how radio waves bounce off different materials. But the real innovation lies in ground-penetrating neutron spectrometers, devices that fire particles into soil and measure how they scatter, revealing hydrogen signatures that betray water's presence. Private companies are miniaturizing these technologies into drill-mounted sensors no larger than a shoebox, allowing robotic prospectors to pinpoint icy veins with surgical precision. Once located, extraction becomes an engineering ballet. Traditional drills would struggle with frozen regolith that's harder than granite at cryogenic temperatures. The solution: hybrid systems like Honeybee Robotics' planetary deep drill, which combines rotary cutting with ultrasonic vibrations to shatter ice without overheating. Another approach uses thermal mining, lowering heated probes that sublimate ice directly into vapor, which is then captured and condensed. Tests in Antarctica's dry valleys, Earth's closest Mars analog, have yielded liters of water per hour using this method. The implications ripple far beyond survival. Water molecules split into hydrogen and oxygen become the building blocks for methane fuel, enabling return trips from Mars without Earth resupply. Underground aquifers could also serve as natural radiation shelters. Imagine water-filled curtains lining habitat walls, absorbing cosmic rays while doubling as emergency reserves. Perhaps most intriguing are recent discoveries of briny liquid water beneath Mars' south pole, hinting at environments where microbial life might persist. Back on Earth, these technologies are already transforming arid regions. In places like Namibia's deserts, portable versions of these drills tap into ancient fossil aquifers, while NASA-funded filtration systems purify contaminated groundwater using space-grade membranes. The same innovations keeping astronauts alive could one day drought-proof entire communities. What makes subterranean water mining so revolutionary isn't just the resources it unlocks, it's the shift from viewing other worlds as barren wastelands to seeing them as landscapes rich with hidden potential. The next generation of explorers won't just visit these worlds, they'll drink from them, fuel their journeys with them, and perhaps even find answers to whether we're alone in the universe, all by digging a little deeper. Underground transportation networks on other worlds could solve one of space colonization's trickiest problems: how to move people and supplies across vast distances without exposing them to deadly radiation or dust storms. While Elon Musk's Hyperloop remains an ambitious Earth-bound project, the principles behind it might find their perfect application beneath the Martian surface. Imagine stepping into a pressurized pod that glides silently through smooth tunnels at hundreds of kilometers per hour, connecting distant habitats in minutes rather than days of dangerous surface travel. This vision is closer to reality than most realize, with engineers already tackling the unique challenges of off-world tunneling. The key advantage lies in the environment itself. Mars' lower gravity means tunnels require less structural reinforcement, while the absence of seismic activity reduces the risk of collapses. Researchers at the Swiss Federal Institute of Technology recently demonstrated how autonomous robots could excavate stable tunnels in simulated Martian soil using nothing but compact heating elements, melting the iron-rich regolith into glassy, self-supporting walls. Unlike Earth's complex geology, the consistent composition of lunar and Martian subsurface layers allows for predictable, efficient digging. Some designs even propose using the excavated material to 3D print station platforms along the route, turning waste into infrastructure. But the real innovation comes in the transit systems themselves. Magnetic levitation trains, perfected in cities like Shanghai, become even more efficient in low-gravity environments where energy costs drop dramatically. Engineers are developing scaled-down versions that could operate in narrower tunnels, with linear induction motors adapted for thin Martian air. Others envision pneumatic tube systems similar to those used in banks or hospitals, but scaled up to transport cargo canisters at near supersonic speeds through vacuum-sealed passages. The European Space Agency's Moonlight project includes concepts for subterranean freight networks where robotic carts follow buried magnetic tracks, moving supplies between bases without human intervention. Pressure management presents fascinating solutions. Instead of maintaining full atmospheric pressure throughout miles of tunnels, engineers propose segmented airlock trains, where passengers remain in sealed compartments while the tunnels themselves stay at minimal pressure. This reduces structural stress and allows smaller emergency systems. Some blueprints show how these transit corridors could double as utility channels, with power lines and water pipes running alongside tracks, all protected from surface extremes. The benefits extend far beyond convenience. Underground networks would enable true planetary economies, allowing specialized habitats, mining outposts, research stations, manufacturing hubs to share resources efficiently. A farming colony near the equator could ship fresh produce to polar ice miners, while emergency crews could reach accident sites in record time. During solar storms, entire populations might evacuate through these tunnels to shielded deep shelters. Back on Earth, these technologies are already influencing disaster-resistant infrastructure. Tokyo's flood prevention system incorporates space-grade tunnel reinforcement, while proposals for Arctic research stations borrow from Mars habitat linkage concepts. The lessons learned underground on other worlds might one day help us build smarter, more connected cities here at home. What makes these subterranean transit dreams so compelling isn't just their practicality, it's how they redefine what planetary colonization means. Instead of isolated outposts, we're envisioning thriving underground metropolises where movement is safe, swift, and seamless. The same tunnels that protect us from alien skies could become the veins that connect humanity's interplanetary future. Space radiation doesn't come with warning signs. It's an invisible threat that could derail humanity's dreams of living beyond Earth. While surface habitats require complex shielding materials to block deadly cosmic rays, nature already provides the perfect solution just beneath our feet. Underground environments act like planetary radiation vests, with layers of rock and soil absorbing harmful particles before they reach human occupants. The numbers are startling. Just 2 meters of lunar regolith provides equivalent protection to Earth's entire atmosphere against solar flares and galactic cosmic radiation. This natural shielding effect is changing how engineers approach extraterrestrial architecture. Instead of building massive lead-lined domes or importing expensive shielding materials from Earth, future colonies might simply burrow into hillsides or expand existing lava tubes. NASA RAD measurements from the Curiosity rover revealed that radiation levels inside Martian caves could be 80% lower than surface exposures. Some proposals suggest covering habitats with regolith-filled bags or using robotic bulldozers to pile loose soil onto prefabricated structures, creating instant protection without complex engineering. What makes these solutions so elegant is their scalability. Unlike fixed shielding systems, underground protection can expand as colonies grow. Deeper tunnels for sleeping quarters, thicker ceilings for medical bays, or layered designs that prioritize safety where it's needed most. Researchers at the University of Washington developed computer models showing how tapered tunnel entrances could deflect radiation while allowing easy access, combining safety and practicality. Other teams are experimenting with radiation labyrinths, zigzagging entrance passages that force particles to lose energy through repeated collisions before reaching living spaces. The implications extend beyond basic survival. Reduced radiation exposure means longer mission durations, healthier astronaut crews, and potentially even safe environments for pregnancy and child development, critical factors for permanent settlements. Underground shielding also solves another major problem: secondary radiation created when cosmic rays strike surface materials, producing dangerous neutron showers. Beneath several meters of regolith, this cascade effect virtually disappears. Perhaps most surprising is how these space technologies are already helping Earth. Radiation shielding techniques developed for Mars are being adapted to protect cancer patients during proton therapy, while regolith simulation studies have led to better materials for nuclear waste storage. The same physics that protects astronauts in lunar caves might one day safeguard communities living near radiation hotspots. As we stare up at the stars dreaming of new worlds, the greatest lesson might be looking down. The underground spaces we once associated with darkness and limitation could become the very thing that allows humanity to step into the light, safely, sustainably, and for generations to come. The air you breathe on Mars tomorrow might come from the same algae that cleaned yesterday's wastewater. Welcome to the revolutionary world of closed-loop underground ecosystems. Unlike the fragile life support systems of traditional space stations that rely on Earth shipments, these bioregenerative habitats function like miniature versions of our planet's own life-sustaining cycles. Picture an underground chamber where every exhaled breath, every drop of sweat, even organic waste gets harvested, broken down, and reborn as fresh oxygen, clean water, and nutrients. Its sustainability pushed to its absolute limit, and it's already being proven in some of Earth's most isolated environments. At the heart of these systems are bioreactors, high-tech descendants of nature's decomposition processes. Specialized microbes feast on human waste, converting it into fertilizer for hydroponic farms, while algae tanks scrub carbon dioxide from the air, releasing oxygen in return. The European Space Agency's LISSA project has spent decades perfecting this dance of microbes and plants, creating a prototype that can recycle 90% of water and 70% of oxygen with near-perfect efficiency. In Arizona's Biosphere 2, researchers demonstrated how tightly integrated ecosystems could maintain breathable air for years despite early challenges. Now, engineers are miniaturizing these concepts for off-world use, with some designs fitting entire life support loops into modular units no larger than a refrigerator. But the real genius lies in diversification. Instead of relying on a single method, smart systems combine multiple approaches for resilience. Imagine an underground habitat where bacterial composting handles solid waste, duckweed ponds purify water, and genetically engineered cyanobacteria produce essential vitamins, all monitored by AI that adjusts ratios in real time. When China's Lunar Palace One experiment sealed volunteers for a year in a closed habitat, they survived on a mix of crops, insects, and microbial protein, proving that variety isn't just healthy, it's a survival necessity. The lessons from these systems could redefine sustainability on Earth, too. Desert cities are already adopting water recycling tech from space research, while vertical farms borrow techniques from lunar agriculture prototypes. What begins as a tool for cosmic survival might end up helping us heal our own planet's strained ecosystems. Perhaps most poetic is how these closed loops mirror Earth's own ancient rhythms, just compressed into steel tanks and monitored by sensors. Future colonists might tend their underground algae gardens like terrestrial farmers care for fields, nurturing the tiny organisms that keep them alive. In the silent darkness beneath an alien sky, these self-renewing ecosystems could become more than machinery. They'd be a living reminder of the world we came from and the ingenuity that lets us thrive beyond it. Buried beneath the frozen surfaces of distant worlds, a new kind of vault is taking shape not for gold or jewels, but for the most precious cargo of all, the building blocks of life itself. Cryogenic storage in space isn't just about keeping things cold. It's about harnessing the natural deep freeze conditions of planetary subsurfaces to preserve everything from genetic libraries to emergency medical supplies with zero energy input. On the Moon, where shadowed craters hover near -250 degrees Celsius year-round, or in Mars' permafrost-rich soil, these underground refrigerators could operate flawlessly for centuries without a single watt of electricity. The science behind these cryovaults is brilliantly simple. By burying storage modules just a few meters down, engineers leverage the incredible insulating properties of regolith. The same loose rocky material that makes lunar dust such a nuisance becomes an ideal thermal blanket when packed tightly. NASA proposed lunar cryogenic depots would use this principle to store liquid oxygen and hydrogen harvested from moon ice, creating orbital fueling stations that could slash the cost of deep space missions. But the applications go far beyond rocket fuel. Imagine disaster-proof gene banks preserving Earth's biodiversity in case of catastrophe, or Noah's Ark modules containing frozen embryos of livestock and crops ready to revive a biosphere on demand. One groundbreaking prototype comes from the Svalbard Global Seed Vault here on Earth, buried deep in Arctic permafrost. It safeguards millions of plant seeds at natural sub-zero temperatures. Space adaptations take this further, with self-sealing canisters that protect samples from micrometeorite impacts and radiation. The European Space Agency's Moon Storage Initiative recently tested ceramic capsules that maintain cryogenic conditions through clever phase change materials, absorbing any stray heat that penetrates the underground chamber. Perhaps most transformative are the medical possibilities. Underground cryolabs could store stem cells for astronaut treatments, preserve engineered microbes for terraforming experiments, or even house emergency organ cultures for deep space crews. Researchers at the Massachusetts Institute of Technology developed a glass-like preservation medium called cryomesh that allows biological samples to survive rapid temperature fluctuations critical for locations where power outages might occur. Private companies are already designing modular vaults the size of coffee tables that could land autonomously, bury themselves, and begin preserving payloads before human arrival. The irony is delicious. These ultra-futuristic technologies work precisely because they embrace the oldest freezer in existence, the cosmic cold of planetary shadows. While Earth-based cryogenics requires complex machinery and constant energy input, off-world vaults turn harsh environments into an asset. Future colonists might one day descend into icy caverns to retrieve the seeds, cells, or fuel that keep their civilization thriving, all thanks to the silent, steadfast chill of the underground. What begins as practical storage could evolve into something far grander, a network of biological waste stations scattered across the solar system, ensuring that life, once rooted in one world, can never be erased from existence. In the perpetual dark of these alien iceboxes, humanity's future might literally be waiting on ice. Picture trying to video call Earth from a Martian base, only to realize there's no cellular tower for millions of miles. While we take global connectivity for granted here on Earth, off-world colonies will need entirely new ways to stay linked, and the answer might lie in turning the ground beneath their feet into a giant communication network. Unlike Earth's satellite-dependent systems, subsurface networks leverage the very rock and soil that shield habitats to transmit data, creating a web of connections as reliable as it is revolutionary. Fiber optic cables, those hair-thin strands of glass that power our internet today, could become the backbone of interplanetary communications just with a twist. Instead of stringing them between poles, engineers propose embedding them directly into tunnel walls during construction. These lunar light pipes would be shielded from surface radiation and micrometeorites by meters of regolith, ensuring uninterrupted data flow even during solar storms. The European Space Agency's Moonlight initiative has already tested specially coated fibers that resist the abrasive lunar dust, while NASA explores self-healing cables filled with liquid polymer that automatically seal minor cracks. But what happens when cables can't reach? That's where nature's own infrastructure comes into play. Scientists at the University of Pennsylvania discovered that low-frequency vibrations can transmit data through solid rock with surprising clarity, like tapping messages through a prison wall but at gigabit speeds. Their prototype seismic modems encode information as subtle tremors, detectable by sensors kilometers away. On Mars, where the crust is seismically quieter than Earth's, these vibrations could travel even farther with less interference. Imagine emergency alerts pulsing through the planet's bedrock during dust storms, or miners receiving real-time geology updates from surface rovers via vibrations in the ore they're extracting. The real breakthrough comes when these systems merge. A hybrid network might use fiber for high-bandwidth tasks like Earth video feeds, while vibration channels serve as backup during repairs or link remote outposts too costly to cable. Some designs even incorporate laser repeaters in tunnel ceilings that bounce signals around corners, creating a literal underground internet where data hops between reflective nodes. Private company Aquarian Space is developing a version for lunar use that combines satellite links with subsurface repeaters, ensuring no base ever goes dark. These technologies aren't just theoretical, they're being battle-tested in Earth's most extreme environments. Deep in Canadian mines, vibration-based systems keep workers connected where radio fails, while Antarctic research stations rely on buried fiber to survive months of isolation. The lessons learned there are proving that connectivity isn't about conquering alien environments, but learning to listen through them. Perhaps most inspiring is how these networks could evolve. Future colonies might tap into natural conductive layers in planetary crusts, turning entire mineral veins into antennae. Others could deploy swarms of communication microdrones that burrow temporary data pathways through soil like digital earthworms. What begins as a survival necessity could blossom into something extraordinary, a subterranean nervous system linking humanity's far-flung outposts into a truly interplanetary community. The greatest irony, while we gaze upward dreaming of interstellar messages, the key to staying connected across worlds might literally be right under our feet. Geothermal energy might be Earth's best-kept secret for sustainable power, but it could become an absolute game-changer on other worlds. While Mars and the Moon don't have the dramatic geysers or bubbling lava flows we see on our planet, they still hold vast reservoirs of heat beneath their surfaces, leftovers from their violent formation billions of years ago. Unlike solar panels that go dark during long lunar nights or dust storms, or nuclear reactors that require rare fuel shipments from Earth, geothermal systems could provide constant, reliable energy by tapping directly into a planet's own internal warmth. The key lies in advanced drilling technologies capable of reaching deep enough to access this heat. On Earth, we already extract geothermal energy from hot rock layers just a few kilometers down, but lower gravity on the Moon and Mars makes drilling even more efficient. Robotic probes could deploy compact, high-temperature drills capable of burrowing through regolith and bedrock, eventually reaching zones where residual heat warms surrounding rock to hundreds of degrees. Once there, closed-loop systems could pump fluid down to absorb that heat, then bring it back up to drive turbines or power Stirling engines, all without requiring massive infrastructure. NASA Kilopower project has already explored small-scale nuclear reactors for space, but geothermal could offer a safer, more scalable alternative with zero radioactive risks. Some of the most promising sites aren't random guesses, they're locations where orbital scans have detected unusual thermal activity. Mars' Tharsis region, home to the solar system's largest volcanoes, might still have pockets of magma just beneath the surface. The Moon's so-called lunar hotspots, areas where surface temperatures stay suspiciously warm even during the frigid two-week night, could indicate accessible geothermal reservoirs. Even icy moons like Europa or Enceladus, with their subsurface oceans kept liquid by tidal heating, might one day host geothermal power stations for far-flung colonies. But the real breakthrough isn't just electricity, it's what else this heat can do. Geothermal systems could double as habitat warmers, melting ice deposits into drinking water, or even fueling greenhouses where warmth from below encourages plant growth without energy-intensive heating lamps. Researchers at Iceland's Hellishay power station, the world's largest geothermal plant, have already demonstrated how captured CO2 can be injected into volcanic basalt and mineralized, a technique that could help future colonies manage their air quality while generating power. Perhaps most exciting is how geothermal energy could enable industries beyond basic survival. Metal smelting, glass production, and chemical processing all require intense heat, something that's expensive to generate with solar or nuclear power but comes naturally from a planet's core. A Martian colony with reliable geothermal access might refine local ores into construction materials, manufacture spare parts on site, or even produce rocket fuel without waiting for Earth resupply. The beauty of geothermal lies in its simplicity. Unlike complex fusion reactors or sprawling solar farms, it works with a planet's natural geology rather than against it. Future colonists might one day stroll past humming turbines powered by the same primordial heat that shaped their new world, proof that sometimes the energy we need isn't above us in the sunlight, but deep below, waiting to be unlocked. Deep beneath the surface of other worlds, a new era of scientific discovery is waiting to unfold in laboratories where silence isn't just golden, it's essential. While surface bases grab headlines, the most groundbreaking research on the Moon or Mars might happen kilometers underground, in facilities designed to escape the constant bombardment of cosmic noise that plagues Earth's own experiments. These subterranean labs offer something priceless, near-perfect stillness, for scientists hunting dark matter, measuring neutrinos, or studying quantum phenomena. That stillness could mean the difference between noise and Nobel Prize-worthy clarity. Take the hunt for dark matter, one of physics' greatest mysteries. Earth's deepest labs, like Italy's Gran Sasso or South Dakota's Sanford Underground Research Facility, bury detectors under mountains of rock to shield them from stray particles that could mimic dark matter signals. On the Moon, where the lack of atmosphere and magnetic field leaves experiments exposed to 10 times more cosmic interference, going underground isn't just helpful, it's mandatory. A lunar lab buried beneath just 10 meters of regolith would enjoy a silence impossible on Earth, free from the vibrations of weather, human activity, or even the planet's own magnetic hum. But it's not just particle physics that benefits. Planetary geologists dream of accessing untouched subsurface layers, pristine records of asteroid impacts, volcanic activity, and maybe even ancient water flows. On Mars, where surface rocks have been sandblasted by dust storms for eons, digging just a few meters down could reveal samples frozen in time for billions of years. Imagine a subterranean cleanroom where drills extract ice cores from Martian glaciers, or where robotic microscopes examine microbial fossils shielded from radiation since the planet's warmer, wetter past. These wouldn't just be labs, they'd be time machines. The architecture of these facilities could revolutionize how we build for science. Instead of hauling heavy shielding materials from Earth, engineers might use local resources to create regolith concrete, mixing lunar soil with binding agents to form ultra-dense walls. Some designs propose lining chambers with water-filled membranes, doubling as radiation shields and emergency water reserves, while others incorporate self-sealing airlocks that use electrostatic fields to trap dust. The European Space Agency's moon base concept includes modular labs that grow as new tunnels are excavated, allowing experiments to expand alongside colonies. What makes these underground labs so compelling isn't just what they block out, but what they enable. Quantum computers, notoriously finicky about vibration and electromagnetic interference, might finally achieve stable operation in the quiet depths of a lunar crater. Biologists could study extremophiles in pressurized chambers mimicking subsurface oceans of icy moons. No asteroid sample return missions required. Even archaeologists might one day sift through the buried ruins of early Martian settlements, assuming we're not the first to build there. The irony is profound. To unlock the universe's biggest secrets, we might need to retreat from the sky into the darkness below. These silent, shielded chambers could become the quietest places in the solar system and the loudest amplifiers of human understanding. When the first underground lab on Mars confirms a theory that rewrites textbooks, it won't just be a win for science. It'll be proof that sometimes you have to go deep to see farther than ever before. When disaster strikes on Mars or the Moon, there won't be any emergency responders racing to the scene, just meters of rock between life and oblivion. That's why subsurface emergency shelters are being reimagined not as last resorts, but as meticulously engineered safe havens, built to withstand the kinds of catastrophes that would turn surface habitats into coffins. Picture a network of reinforced chambers hidden beneath a colony's main living quarters, stocked with oxygen recyclers, medical kits, and enough rations to outlast weeks of lethal solar storms or choking dust clouds. These aren't just basements, they're high-tech lifeboats buried in solid rock. The design challenges are unlike anything on Earth. A Martian shelter must handle two opposing nightmares: sudden solar particle events that bombard surfaces with radiation, and months-long global dust storms that blot out sunlight and plunge temperatures to deadly lows. NASA RD data shows that during a solar storm, unprotected astronauts could absorb a year's worth of radiation in just hours, but descend 3 meters beneath the surface and exposure drops to near zero. Engineers are testing modular shelter pods that deploy automatically when radiation sensors spike, inflating airtight membranes lined with water-filled pockets, a material that's lightweight for transport but brilliantly effective at absorbing energetic particles. What makes these shelters revolutionary is their dual-use philosophy. During normal operations, they might serve as storage vaults or low-traffic workspaces. But when alarms sound, folding bunks descend from walls, CO2 scrubbers kick into overdrive, and triple-locked supply cabinets rotate open to reveal emergency gear. Some prototypes even incorporate panic gardens, compact hydroponic units with fast-growing algae and greens to supplement rations if rescue takes longer than expected. The European Space Agency's Shelter project recently demonstrated a version that recycles urine into drinking water using compact distillation tech borrowed from submarine systems. The real proving grounds, Earth's own extreme environments. In Antarctica's Concordia station, where winter temperatures mimic Mars' cold and isolation, scientists train in mock subsurface bunkers, testing how crews handle confinement when cut off from surface supply runs. Meanwhile, volcanic tunnels in Iceland host pressure simulations, where engineers study how shelter walls hold up against sudden decompression events. These trials reveal unexpected insights like how certain lighting frequencies can prevent circadian rhythm disruption during extended lockdowns, or why shelter interiors should avoid right angles to reduce psychological stress. But the most ingenious solutions come from repurposing local materials. Instead of hauling heavy shielding from Earth, some designs use regolith itself as protection. Robotic 3D printers could rapidly pile loose soil into domes over pre-positioned shelter modules, creating instant radiation barriers. Others propose flooding the gaps between double-walled structures with ice harvested from subsurface deposits, a material that shields against radiation while also serving as an emergency water reserve when melted. The ultimate goal, making these shelters obsolete through redundancy. Future colonies might resemble distributed networks where every major habitat connects to multiple safe rooms via pressurized tunnels, ensuring no one is ever more than minutes from safety. It's a stark reminder that in space, survival isn't about heroic last stands, it's about smart preparation, smart engineering, and the humility to recognize that sometimes the safest place to be is deep underground, waiting out the storm. Living beneath the surface of another world might keep colonists safe from radiation, but how do you protect their minds from the crushing weight of endless rock overhead? That's where virtual reality steps in, not as a luxury but as a psychological lifeline. Imagine strapping on a headset and instantly standing on a sunlit beach, watching waves roll in, or hiking through a forest where birdsong drowns out the silence of your underground chamber. These aren't just escapist fantasies, they're carefully engineered tools to trick the brain into believing it's somewhere else entirely. and they could mean the difference between sanity and breakdown during years-long missions. The science behind this is surprisingly profound. Studies in Antarctic isolation and underwater habitats reveal that humans need visual variety to stay mentally balanced, something painfully absent in windowless tunnels. NASA HERA program found that even simple projections of Earth scenes reduced stress markers in test subjects by over 30%. But next-gen VR goes far beyond static images. Researchers at Stanford's Virtual Human Interaction Lab are developing dynamic environments that respond to movement, letting astronauts walk through digitally reconstructed memories of home or explore fantastical landscapes designed to stimulate curiosity and joy. Some prototypes even incorporate haptic floors that mimic grass or sand underfoot, while scent dispensers release pine or salt air to complete the illusion. What makes these systems revolutionary isn't just their realism, it's their adaptability. AI could monitor an astronaut's biometrics, adjusting environments in real time, swapping a serene meadow for a bustling cityscape if it detects signs of loneliness, or triggering a sudden rainstorm to break the monotony of perfect weather. There's even talk of shared VR spaces, where crews from different bases meet virtually, playing games or attending concerts to maintain social bonds across planetary distances. The European Space Agency's Lunar 2 project includes a communal window room where wall-sized screens stream live Earth views with a 20-minute delay or generate alien vistas based on geological data from surface rovers. But the most ingenious solutions address the root of space psychology's biggest challenge: time perception. Without sunrise cues, circadian rhythms unravel. Some VR systems now incorporate dynamic lighting that subtly shifts from dawn to dusk, while others use gamified calendars to help crews visualize mission progress like a growing virtual tree that blossoms as homecoming approaches. Others might project stars onto tunnel ceilings, not just for beauty but to reinforce that this underground existence is temporary, a stepping stone, not a tomb. The irony: these technologies are already healing minds on Earth. Burn units use VR nature scenes to distract patients from pain, while submarines and Arctic stations employ similar systems to combat winter depression. The same tools keeping astronauts sane beneath Martian soil might one day help miners, disaster survivors, or anyone forced to live in the shadows. Virtual reality won't just decorate underground life, it'll redefine it, transforming sterile tunnels into canvases for the human spirit. When the first Mars colonists finally return to the surface after months below, they might just miss those digital sunsets. Launching rockets from underground might sound like science fiction, but it could solve one of space exploration's most dangerous problems: the perilous first few seconds of ascent. Picture this: instead of a rocket sitting exposed on a surface pad, vulnerable to dust storms, micrometeorites, or high winds, it waits safely inside a deep vertical shaft, shielded by meters of rock. When the countdown hits zero, electromagnetic rails or compressed air catapults hurl it upward at breathtaking speed, clearing the tunnel mouth before its engines even ignite. This isn't just theoretical. Engineers are already testing prototypes that could make underground spaceports the futuristic norm for launches on the Moon, Mars, and beyond. The physics behind this approach is surprisingly practical. On airless worlds like the Moon, traditional launch pads face a unique challenge. Without atmosphere to slow them down, dust and debris kicked up during liftoff can travel for kilometers, potentially damaging nearby infrastructure. An underground launch system solves this by containing the initial burst of exhaust within the tunnel, directing it through specialized vents. The European Space Agency's Star-Tiger project recently demonstrated how a scaled-down rocket could be electromagnetically accelerated to supersonic speeds inside a vacuum chamber, eliminating the need for early-stage engine burns that waste precious fuel fighting gravity. But the real innovation lies in the launch mechanisms themselves. Electromagnetic mass drivers similar to those proposed for Earth-based space elevators could propel rockets upward using magnetic repulsion, reaching velocities where engines only need to fire once the vehicle is already airborne. Alternatively, pneumatic systems might use compressed gas to pop rockets out of their shafts like corks from a bottle. A concept private startup Spin Launch is already testing for small payloads on Earth. These methods aren't just safer, they're more efficient. By offloading the initial acceleration to ground-based systems, rockets can carry less fuel, freeing up weight for scientific instruments or crew supplies. Underground spaceports also offer strategic advantages. Their concealed nature makes them harder to target in potential conflicts, while their modular design allows for rapid expansion as colony needs grow. Imagine a lunar base with multiple launch shafts, some dedicated to cargo, others to crewed missions, all connected by subterranean rail lines that transport rockets horizontally for maintenance before rolling them vertically for launch. The tunnels themselves could double as storage for fuel harvested from local ice deposits, creating a seamless pipeline from resource extraction to liftoff. Perhaps most intriguing is how these designs adapt to different worlds. On Mars, where thin atmosphere still poses aerodynamic challenges, launch tunnels might incorporate aerodynamic fairings that peel away during ascent. For icy moons like Europa, heated boreholes could prevent refreezing between launches. Even Earth could benefit. Desert launch sites might bury their infrastructure to protect against sandstorms, while island spaceports could use offshore vertical shafts to minimize noise pollution. The vision is clear. By moving launch operations underground, we're not just protecting rockets, we're redefining what space access looks like. When the first Martian colonists watch their supply ship streak upward from beneath the surface, they'll witness more than a clever engineering solution. They'll see proof that sometimes the best way to reach the stars is to start from the depths. Microbial mining sounds like something out of a mad scientist's lab, but it's already happening here on Earth, and it could revolutionize how we harvest resources in space. Picture this: instead of noisy drills and massive excavators tearing up the lunar surface, armies of microscopic workers silently dissolve rocks, releasing valuable metals drop by drop. These aren't robots, they're living organisms, bacteria like Acidotheobacillus and Leptospirillum, which naturally break down ores to access nutrients. On Earth, they're used to extract copper and gold from low-grade deposits. On the Moon or Mars, they might become the invisible workforce that turns barren caves into bustling resource hubs. The process, called bioleaching, is surprisingly straightforward. These bacteria thrive in acidic environments, producing compounds that dissolve metallic bonds in surrounding rock. In space, where traditional mining would require hauling heavy equipment across millions of miles, bioleaching offers a lightweight alternative. Imagine stacking trays of crushed regolith inside pressurized underground chambers, then flooding them with bacterial solutions. Over weeks or months, the microbes would gradually release metals like iron, titanium, or even rare earth elements critical for everything from electronics to rocket parts into the liquid, which could then be filtered and processed. NASA's BioRock experiment aboard the International Space Station proved these organisms can function in microgravity, setting the stage for off-world applications. But the real genius lies in scalability. Unlike mechanical mining, which requires constant energy input, bacterial reactors are largely self-sustaining once activated. Some designs propose using genetically modified strains tailored to specific minerals or extreme conditions, like the perchlorate-rich soil of Mars. Others envision living filters, where bacteria not only extract metals but also purify them, leaving behind cleaner end products. The European Space Agency's Bio-Asteroid project demonstrated how fungal bacterial combos could even break down asteroid material, hinting at a future where deep space refineries run on biology rather than brute force. The environmental benefits can't be overstated. Traditional mining scars landscapes and generates toxic runoff, a non-starter on worlds we aim to preserve for science. Bioleaching, by contrast, leaves tunnels intact and produces minimal waste. Closed-loop systems could recycle the acidic solutions indefinitely, with spent bacteria becoming fertilizer for underground farms. It's a rare win-win, gentle enough for planetary protection yet potent enough to fuel an interplanetary economy. Perhaps most exciting is how this tech is already evolving on Earth. Companies like BioSigma in Chile use bacterial mining to recover copper from tailings, while researchers in Canada experiment with microbes that clean up mining pollution. The lessons learned there, optimizing bacterial strains, speeding up reaction times, directly inform space applications. Future colonists might deploy bioreactors like breweries, culturing local strains adapted to alien geology. In the grand quest to live off the land beyond Earth, we've overlooked our smallest potential allies. These unassuming microorganisms could hold the key to sustainable space industry, proving once again that nature's solutions often outshine our flashiest machines. When the first Martian refinery ships metals to orbit, its invisible workforce won't demand pay, just the right conditions to do what they've done for billions of years: transform stone into treasure. The ground beneath our feet isn't as solid as it seems, especially on other worlds. While Mars trembles with subtle marsquawks and the Moon shakes with deep seismic tides, these alien tremors could pose silent threats to future colonies. Without the kind of global monitoring networks we take for granted on Earth, a single unexpected quake could crack pressurized habitats or collapse carefully dug tunnels. That's why scientists are racing to deploy networks of underground seismometers, not just to study these phenomena, but to turn them into early warning systems that could save lives. Mars quakes are particularly mysterious. NASA InSight lander recorded hundreds during its mission, some lasting over an hour, far longer than typical Earth tremors. But unlike our planet, where quakes stem from shifting tectonic plates, Martian seismic activity comes from the planet's gradual cooling and contraction, causing its crust to fracture like a drying mudflat. The Moon, meanwhile, experiences deeper moonquakes triggered by Earth's gravitational pull, some strong enough to topple unsecured equipment. Both environments share a critical vulnerability. Without multiple sensors working in unison, it's nearly impossible to pinpoint where or when the next big shake will hit. That's where subterranean sensor arrays come in. By burying seismometers in networks across colony sites, engineers could detect initial tremors microseconds before the damaging waves arrive, enough time to seal bulkheads, shut off fragile systems, or evacuate vulnerable areas. The European Space Agency's lunar seismic network concept envisions planting self-deploying spikes that hammer into regolith like high-tech tent pegs, each containing ultra-sensitive motion detectors linked by underground fiber optic cables. On Mars, similar systems might use compact drones to distribute sensors across lava tubes, creating a web of surveillance that maps fault lines in unprecedented detail. The technology isn't just theoretical. In Antarctica's dry valleys, one of Earth's closest Mars analogs researchers from the University of Tokyo tested compact seismometers designed to operate in extreme cold, buried under layers of permafrost to filter out wind noise. Meanwhile, mining companies worldwide already use real-time seismic monitoring to predict collapses in underground tunnels, proving the concept can save lives. These Earth-bound experiments reveal a surprising truth. The same vibrations that signal danger can also become tools for safety if we learn to listen closely enough. What makes these systems truly revolutionary is their dual purpose. Beyond disaster prevention, they could unlock planetary secrets, mapping underground water deposits by how seismic waves slow when passing through ice, or revealing magma pockets that might one day fuel geothermal energy. Future colonists might check daily seismic reports like weather forecasts, planning activities around periods of low tectonic risk. The irony is profound. To thrive on worlds we once saw as dead and static, we'll need to embrace their hidden vibrations. Those faint tremors beneath our boots won't just be threats. They'll be conversations telling us where to build, where to dig, and when to take cover. In the silence of alien caves, listening carefully might be the smartest survival skill we bring. Inflatable habitats sound like something from a child's playroom, but beneath the surface of other worlds, they could be the key to rapid, adaptable colonization. Picture a massive balloon, not the colorful party kind, but a high-tech membrane stronger than Kevlar unfurling inside a lunar lava tube. As it inflates, its walls press against the surrounding rock, forming a perfect seal that turns a barren cavern into a pressurized living space in hours, not years. This isn't just a thought experiment. Companies like Sixa at the University of Houston are already testing prototypes that could one day shelter astronauts with technology simpler than a bicycle pump. The genius of subsurface balloons lies in their efficiency. Traditional rigid habitats require heavy materials shipped from Earth at astronomical cost, but inflatables can be packed flat into a single lander, then expanded to volumes 10 times their storage size. NASA Bigelow Expandable Activity Module proved the concept in orbit, surviving 2 years attached to the International Space Station despite micrometeorite risks. Underground, shielded by meters of rock, these structures would face even fewer threats while offering instant radiation protection. Some designs incorporate self-healing polymers that automatically seal small punctures, while others use multi-layer membranes filled with foam or aerogel for insulation against extreme temperatures. But the real innovation isn't just the balloons themselves, it's how they interact with their environment. Engineers are exploring regolith anchoring, where the weight of overlying soil actually strengthens the habitat. As a balloon inflates, it could deploy external straps that grip the cavern walls like a climbing harness, distributing pressure evenly to prevent collapses. Others propose spraying the inflated structures with a slurry of local dust and binding agents, creating a hybrid shell that's part fabric, part geology. The European Space Agency's Lava Hive project even imagines interconnected balloon modules, allowing colonies to expand organically by inflating new chambers as needed. What makes these designs so transformative is their versatility. A single system could serve as emergency shelter during solar storms, temporary housing for rotating crews, or even greenhouses with translucent upper sections channeling sunlight through reflective tunnels. During the 2023 Moon Village Association Symposium, researchers demonstrated how inflatable pods could be pre-equipped with fold-out furniture, solar-powered air recyclers, and even hydroponic racks, essentially shipping as flat-packed homes ready for instant occupation. The implications for exploration are staggering. Imagine a Mars mission landing near a lava tube complex, deploying a dozen inflatables in days, and establishing a functional base before Earth even confirms their safe arrival. Or lunar miners setting up pop-up workshops deep underground, then deflating and relocating them as resources are exhausted. Unlike static habitats, these structures allow for true adaptability, the closest thing to packing light for another world. Yet the most poetic detail might be how they echo nature. Just as certain deep-sea creatures use swim bladders to withstand crushing pressures, these habitats leverage flexible membranes to tame alien environments. When the first colonists float a balloon into the darkness of a Martian cave and watch it swell into their new home, they won't just be deploying technology. They'll be proving that sometimes the softest solutions are the strongest. Living in low gravity might look fun in videos floating through corridors, lifting heavy objects with ease, but our bodies pay a terrible price for that weightlessness. Astronauts returning from long missions often struggle with weakened bones, atrophied muscles, and even vision changes caused by fluid shifts in microgravity. For brief space station stays, rigorous daily exercise can mitigate some damage, but future Mars colonists facing years in reduced gravity need a better solution. That's where underground centrifuges come in, spinning habitats that use centrifugal force to mimic Earth's gravity, not as a futuristic luxury, but as a medical necessity disguised as architecture. The science behind these rotating chambers is surprisingly straightforward. Just like spinning a bucket of water fast enough keeps the liquid pinned to the bottom, a circular habitat rotating at the right speed could generate enough outward force to simulate Earth-like gravity along its outer walls. NASA's early experiments with small centrifuges on the International Space Station proved the concept works. Test subjects experienced measurable physiological benefits after just 30 minutes of daily spin therapy. Scaling this up to full-time living spaces presents engineering challenges, but underground environments offer unique advantages. Lava tubes or excavated tunnels provide natural structural support for massive rotating rings, eliminating the need for bulky external frameworks. The European Space Agency's Moon Village concept includes a centrifuge module buried beneath regolith, where 20-meter diameter rings spin at 4 revolutions per minute, fast enough to create lunar gravity along the rim, but slow enough to avoid motion sickness. What makes these designs revolutionary isn't just their size, it's how they integrate with daily life. Picture a Martian base where sleeping quarters, gyms, and medical bays wrap around the outer edge of a spinning drum, while stationary core areas house laboratories and storage. Astronauts might spend their workdays in low gravity conducting experiments, then retreat to the spinning section to eat, exercise, and sleep under Earth-like conditions. Some prototypes even feature adjustable rotation speeds, allowing gradual adaptation for new arrivals or customized therapy for those particularly affected by bone loss. The real breakthrough comes from combining these systems with other underground technologies. Centrifugal habitats could share structural walls with geothermal power plants, their rotation powered by the same thermal energy driving the colony. Excavated regolith might line the spinning chambers as radiation shielding, while 3D printed tracks along the interior could guide magnetic levitation systems for near frictionless rotation. Early tests at Blue Origin's Orbital Reef facility show how modular segments could be added to expand the ring as a colony grows, like adding cars to a cosmic merry-go-round. Critics argue the energy costs might be prohibitive, but lunar and Martian gravity require less rotational force than full Earth simulation, dramatically reducing power needs. Others worry about mechanical failures, though redundant bearing systems and emergency brakes make catastrophic stops unlikely. The greater challenge might be psychological, adjusting to curved floors where down is always outward, or transitioning between spinning and stationary zones. Yet Antarctic winter over crews already adapt to similarly disorienting light cycles, proving humans can handle radical environmental shifts with proper design. What begins as a health safeguard could transform into something grander: underground cityscapes where entire districts rotate at different speeds, each tailored to specific needs. Farms might spin faster to encourage plant growth, while factories operate in low-G zones where delicate manufacturing benefits from reduced weight. Over generations, these subterranean centrifuges could allow human bodies to remain Earth-ready even as our civilization becomes multiplanetary. The irony is profound. To stay grounded as a species, we may need to keep spinning like tops in the darkness beneath alien worlds. When the first Mars-born child grows up without their bones crumbling in low gravity, they'll owe their strength to these unassuming rotating rings, proof that sometimes moving in circles is the straightest path forward. Imagine an entire internet's worth of data humming silently beneath the surface of Mars, server racks glowing in the darkness, not in some fragile surface dome, but nestled safely within tunnels where the planet itself becomes the ultimate firewall. This is the future of off-world computing, where subsurface data centers leverage alien geology to solve problems Earth-based tech still struggles with. Traditional server farms are energy hogs, requiring massive cooling systems to prevent overheating. But on the Moon or Mars, the natural chill of underground environments, often hovering around -60 degrees Celsius, could slash cooling needs by up to 90%. NASA's Lunar Crater Radio Telescope project already exploits this principle, using permanently shadowed craters as natural freezers for sensitive equipment. The real magic lies in radiation shielding, cosmic rays that fry surface electronics barely penetrate a few meters of regolith. Companies like Microsoft have experimented with underwater data centers off Earth's coasts, proving the concept of naturally cooled, shielded server farms. Translate that to Mars, and you could have an entire planetary internet backbone protected by the very ground it's buried in. These wouldn't just be storage vaults, they'd be neural hubs for colony AI, processing real-time weather predictions for dust storms, managing life support systems, or even simulating terraforming models. The European Space Agency's Moonlight program envisions lunar data centers acting as relays for Earth communications, bouncing signals through subsurface fiber optic networks to avoid surface interference. But the most groundbreaking application might be in situ resource utilization. Future servers could be 3D printed from local metals extracted through bioleaching, their chips fabricated in underground cleanrooms using silicon from Martian sand. Quantum computers, notoriously finicky about vibration and electromagnetic noise, might find their ideal home in the seismic stillness of lunar basalt chambers. Early prototypes like Japan's Fugaku supercomputer already use immersion cooling, a technique where servers are bathed in non-conductive fluid that could be adapted for low-gravity environments with self-sealing tanks. What begins as practical infrastructure could evolve into something extraordinary: the first extraterrestrial cloud platforms. Martian startups might one day rent server space in lava tube colocation facilities, their data safer from solar flares than any Earth-based competitor. Archaeologists could upload entire planetary surveys to subsurface servers, preserving them for centuries in time capsule vaults. And when the first interstellar probes send back their torrents of data, it won't be surface antennas straining to receive them, it'll be buried supercomputers, cool and patient in the dark, turning cosmic whispers into human knowledge. The irony is profound. Our most advanced technology might ultimately thrive where humanity's earliest ancestors sought shelter, in the protective embrace of stone and soil. When future colonists stream high-definition footage of Martian sunsets to loved ones back on Earth, the signal won't come from some vulnerable surface tower. It'll rise from the depths of proof that in the digital age, even the cloud has roots. From habitats to highways, the underground revolution is reshaping how we think about space exploration, not with flashy rockets or gleaming surface domes, but through quiet, relentless innovation beneath the surface. These 21 technologies prove something profound. The solutions to our greatest extraterrestrial challenges won't always come from looking up, but from digging deeper. Just a decade ago, subterranean space tech seemed like the stuff of novels today. It's happening in labs, lava tubes, and simulation sites worldwide. Autonomous diggers are chewing through simulated Martian soil. Inflatable habitats are unfurling in desert caverns, and microbial miners are already extracting metals from asteroid-like rocks. The future isn't just approaching, it's tunneling toward us. What's most striking isn't any single invention, but how these systems interconnect. Underground farms feed colonists while recycling their waste into fertilizer. Tunnels carved by robotic moles double as radiation shields and transit routes. Geothermal plants power the very centrifuges that keep astronaut bones strong. This isn't a collection of gadgets, it's an ecosystem of technologies that amplify each other, turning hostile environments into livable spaces, one innovation at a time. The lessons learned here ripple back to Earth too. Disaster-proof underground storage, sustainable closed-loop agriculture, and resilient subterranean infrastructure could transform how we face climate change and resource shortages. The shift in mindset is just as revolutionary as the tech itself. We're moving from seeing planetary surfaces as our only option to recognizing the potential hidden below, a lesson nature taught us long ago. From ants to moles, countless species thrive underground for protection and efficiency. Now, humanity is learning that same wisdom, blending cutting-edge engineering with the oldest shelter strategy in existence. The irony is beautiful. To become a spacefaring civilization, we must embrace our inner troglodyte. So which of these breakthroughs resonates with you? The elegance of subterranean energy storage, the quiet genius of microbial mining, or perhaps the psychological cleverness of VR windows in sunless tunnels? Share your pick in the comments. We're all part of this conversation. And if you've enjoyed this descent into the future, hit subscribe for more explorations of how technology is rewriting the rules of what's possible. The underground space age isn't coming, it's already here, waiting just beneath the surface of our awareness. All we have to do is dig in.